everyone. Thanks for joining. My name is Basat, and I'll be telling you about how to send a real number with just one bit. And this is a joint work with Shay Vargaftik and Michael Mitzenmacher. And in our setting, we have two parties, Buffy and Angel, the vampire slayers, if you're familiar. And Buffy has a number, X between 0 and 1, right? So she wants to communicate it to Angel, but she can only send a one-bit message, capital X. And Angel then wants to estimate the input number, and the goal of this protocol is to minimize the cost, which we define as the expected squared error of the estimate taken for the worst case input X. And in some cases, we would also want the estimate to be unbiased, in which case optimizing the cost is the same as minimizing the variance. Okay, so let me give you an application for that, and that's federated learning. And in federated learning, we have multiple clients that participate in the learning, and in each round, we pick a subset of these clients, and we send the global model for each of them. So the clients have their local data, they take the model weights, they compute the local gradient, and then they send it back to the server. The server takes all the local gradients, average them, and compute the new weights, and the new round begins, and so on. And in the machine learning community, a lot of focus was given to the setting where we want to send each number with just one bit. And today we're gonna have a theoretical analysis of this one bit setting where we have a single number X, a single bit message, capital X, and that's it. And it sounds easy, right? Like how hard can it be? Okay, we'll get to that. So first, some bad news. It turns out that standard algorithms are already optimal. The first standard algorithm is called a randomized rounding or stochastic quantization. It's very natural. Buffy will just send a Bernoulli random variable with mean small x, and Angel will estimate x as the message capital X, right? So basically rounding things to either 0 or 1 in an unbiased manner. And this is what the variance looks like for this algorithm as a function of the input x. And we said we care about the worst case. So the worst case is when x equals 1/2, where we get a variance of 1/4. Now, we prove a theorem that says that any unbiased algorithm must have a variance of at least 1/4, even if we restrict the input x to just 0, 1/2, or 1. Right? So in that sense, it's optimal. A second standard algorithm is called deterministic rounding. And here, Buffy will send 1 if x is more than 1/2. And Angel will estimate x as 1/4 if x is lower than 1/2, like in this example, or 3/4 if it was larger. So this is what the expected squared error looks like. So we have 0 error for 1/4 and 3/4, but we have squared error of 1/16 when x equals 0, 1/2, or 1. And it turns out that, again, any algorithm must have an expected squared error of 1/16, even if x is restricted to the 3 values. Right? And both of these theorems have an asterisk there saying that it's true when there's no shared randomness. And now we'll get to what you can do with shared randomness, but first, how do we define shared randomness? So I'm sure you can imagine that all it means is that Buffy and Angel can make the same coin flips, get the same result H, right? And this can be achieved, for example, if they have the same pseudo-random generator seed. But we have to keep in mind that shared randomness can be costly, so we may want to look at what happens if we have just a small number of bits. Now, sending numbers with shared randomness is not really new. Actually, it's almost 60 years old. So subtractive dithering is a protocol that was first proposed for quantizing photos and speech, and lately it's been used for federated machine learning. And in subtractive dithering, they both generate something called the noise H, which is a number uniformly distributed between -1/2 and 1/2. And Buffy sends 1 if x plus the noise is larger than 1/2 and 0 otherwise. And Angel takes the message x and subtract the noise from it. So in this sense, it's subtractive. So Buffy adds the noise before sending it, and Angel subtracts it when estimating the number, right? So this is what it looks like, right? So we don't compare the input x to 1/2 like we did in deterministic rounding. We first add the noise to it. We get x plus h, and in this example, x plus h is larger than 1/2. Then Buffy sends and Angel takes this one, subtracts the noise, and this gives the estimate. Now, it's known that subtractive dithering has an estimate that's distributed uniformly between x minus 1/2 and x plus 1/2. In particular, it means that the algorithm is unbiased and its variance is 1/12. And subtractive is really great, but it requires generating this real number h, which means unbounded shared randomness. And what we're going to do next is we're going to look at what happens if you have just one shared random bit, right? And before we do that, let's step back and look again at randomized rounding, right? So in randomized rounding, we round things to either 0 or 1. And one way to implement randomized rounding is that Alice can draw a uniform 0/1 random variable R using private randomness. Right? And it can send the message 1 if X is larger than R. And this gives this variance figure that we saw. Now, what you can do when you do have this one bit of shared randomness, right? So H is now going to be either 0 or 1, is that Buffy will still use private randomness, and it will send 1 if X is larger than the average of R and H. Angel will estimate X as the message capital X plus H minus its expectation over 2. So this looks like a weird algorithm, right? When H equals 0, we will round X to either -1/4 or 3/4. When H equals 1, we will round X to either 1/4 or 5/4. Right? So why is this better than just rounding it to 0, 1? Well, let's see. So let's see what happens when H equals 0, right? So if you look at Buffy's algorithm, you can see that if X is larger than 1/2, then Buffy will surely send 1 and Angel will estimate X at 3/4, right? So it means that we have 0 error for 3/4, and if X was smaller than 1/2, we have like a randomized rounding like algorithm going on. And similarly, when H equals 1, then if X was smaller than 1/2, Buffy will surely send 0 and Angel will estimate it as 1/4, right? So now what's happened is that on average, like in expectation, you can just average these two figures, and what you would get is an algorithm whose worst case variance is at most 1/8. So we improve the variance by a factor of 2 by using a single bit of shared randomness, right? And we can generalize this to 2 bits, 8 bits, and more. And it turns out that with just 8 bits, it kind of looks like subtractive dithering, like a horizontal line. That's not entirely true. Like if you zoom in enough, you would see that it's not. But our algorithm provides a spectrum between randomized rounding, which is what you get with when L equals 0, and subtractive dithering, which is when the number of shared random bits tends to infinity. Now, what we're going to do next is we're going to talk about how we can adapt subtractive dithering, which was the algorithm with the lowest variance in the unbiased world, and we can use it to improve over deterministic rounding, which was the best biased algorithm when there's no shared randomness, right? And the way to do that is to change the estimation function that Angel uses, right? And what we propose is that instead of just subtracting the noise, the estimate should be a linear combination between the message and the shared randomness. So we slightly changed Buffy's algorithm too, right? So H would now be a number between 0 and 1, and Buffy will just send 1 if X is larger than H. And Angel would use this convex combination between the shared randomness and the message X. And the intuition here is that when when H is large, then the threshold is higher, it's less likely to send 1, and then we should estimate X as being a larger number, right? So if we optimize this algorithm, like this weight alpha, we can actually get a cost that's already much better than deterministic rounding. Right? Now, before we're going to talk about other algorithms, I want to give you a characterization of all the reasonable algorithms in this domain. Right? And I claim that it's enough to look at algorithms as a pair of two functions, t and z0, that maps numbers between 0 and 1 to numbers between 0 and 1. And the algorithm would just be that Buffy sends 1 if X is larger than the threshold of H, d of H. And Angel will estimate X as Z1 of H if it receives 1, if the message was 1, and Z0 of H if the message was 0. And actually, Z1 of H would just be like the symmetric analog of Z0. So Z1 of H would be 1 minus Z0 at 1 minus H, right? So it's enough to look at just these two functions, T and Z0. For example, the previous algorithm with the convex combination, we can express it as T of H equals H and Z0 of H equals alpha H. Right? So this is what it looks like, right? So here you have deterministic rounding, which is, deterministic. So it has a fixed threshold of 1/2, right? It sends 1 if X was more than 1/2. And if we receive 0, we always estimate X as 1/4. And in contrast, this convex combination approach has both the threshold and the estimate function increase linearly in H. Okay, and one thing I want to mention is that even these two functions are not entirely independent. So any reasonable algorithm would satisfy that the threshold given the shared randomness H has to be exactly the midpoint between the two possible estimates, Z0 of H and Z1 of H. And the idea is that we know that if we know that this is how Angel is going to interpret our message and estimate X, we will send a message that minimizes the error. Right? Okay, so let me give you some improvement over this convex combination idea. And the idea here is what we call deterministic edge rounding, which will basically say if the number is too small or too large, just round it deterministically. So instead of looking at numbers in the range 0, 1, I just look at a smaller range. Right? And what I mean by that is that, and in between, like between these two, we will still run the same convex combination. And what I mean by that is that when Buffy sends the message, it will always send 0 if X is small. It will always send 1 if X is large. And in between, we will run the same subtractive dithering with a convex combination, right? So Angel's algorithm is exactly the same. So once again, we can express this algorithm as a threshold function, a Z0 function, And this is what it looks like, right? So now the estimate function is exactly the same. So the Z0 function is the same, but the threshold now doesn't start from 0, doesn't go all the way to 1. It's bounded in a smaller range. And it turns out that this algorithm doesn't actually improve the cost, right? It looks something like this. If you optimize the parameters, right? So we can see that at the worst case input, we actually get the same expected squared error as if we were not rounding the edges, right? So why am I telling you about this? Like, why is this algorithm interesting, right? So let's look at what happens when we use a finite number of shared random bits to implement, right? And what I mean by that is that h would now be an integer between 0 and 2 to the n minus 1. And we will need to scale both the sending and the estimate, right? So we will divide by this factor of 2 to the n minus 1. And what we get is an algorithm that the more bits you give it, the more it looks like the version with the continuous h. But what's interesting here is that if we zoom in on it, we can actually see that the algorithm improves from 1 bit to 2 bits and then to 3 bits. But then the cost starts increasing. So 4 bits is worse, and continuous h value is even worse, right? So what we get is that if we use just 3 random bits, we can actually reduce the cost compared to this convex combination approach. Okay, so what we're gonna do now is we're gonna try to see what the optimal algorithm would look like. And actually, we don't know that. In the optimal algorithm, T and Z0 have some weird shapes, like we show in the paper, and we don't know what the optimal algorithm looks like, but if we restrict the number of shared random bits, then it turns out we can find the optimal algorithm that uses that number of bits, right? And why is that? So the idea here is that if you fix the shared randomness, right, then Angel has two possible estimates, Z0 of H, Z1 of H. And the worst case error is going to be the X value that's right in the middle, right? We also need to take care of 0 and 1, but other than that, it could only be the X value that's in the middle. And what it means is that if we use a finite number of bits L, then we can look at a finite number of possible values for X. And by bounding the arrow there, we can bound the arrow for any X in 0, 1. And now that we have this idea, we can use a quadratic solver with something like 2 to the L variables and 2 to the L inequalities and approximate the optimal solution, right? And that actually brings the cost down to something like you can see in this table, like 0.04599. And what's interesting here is that it almost matches the lower bound, like we got 3 decimal digits, right? And now I'm going to tell you a bit about this lower bound, right? So we have a near optimal algorithm at lower bound. Okay, so for the lower bound, we use Yale's minimax principle that tells us that the cost of any randomized algorithm is going to be at least the expected squared error of the best deterministic algorithm. But now the expectation is not with respect to the algorithm, it's with respect to an input distribution Q, right? So a deterministic algorithm is basically defined as 2 values, what Angel estimates given 0, what Angel estimates giving the message 1. And we have this input distribution Q. And if we can find a distribution that and compute this value, we get a lower bound on the cost of any random algorithm, right? So we propose to look at the following distribution. It has two parameters, A and W, and in this distribution, with probability W, X is going to be 0. With probability W, X is going to be 1, and otherwise, it's going to be uniformly distributed between A and 1 minus A. Now, even for this distribution, we don't know what the optimal deterministic algorithm looks like. We conjecture that there exists an optimal algorithm for it, in which either the estimate given the message 1 is 1 minus the estimate given the message 0, or the estimate would be just 1. And I'm going to emphasize here that the lower bound would hold even if the conjecture is false, right? But let's see how we use this conjecture. So using this conjecture, we can find the optimal A and W values that maximize the expected squared error of the best deterministic algorithm from this family that satisfy 1 or 2. Right? And now that we know what these values are, we can verify that no algorithm, even outside this family, no deterministic algorithm can improve on this distribution. And the way we do that is we take the distribution and we discretize it. We build a discrete distribution on endpoints that resembles this distribution. And then we run a deterministic k-means algorithm for k equal to on this discrete distribution to compute what's the optimal deterministic algorithm for this discrete distribution, right? And we said like any distribution would give a lower bound, so this discrete distribution also gives a lower bound, and as n tends to infinity, this discrete distribution converges to this QAW distribution, and this is how we get the lower bound. Okay, so what are the takeaways here? Shared randomness helps in both biased and unbiased settings. Even a small number of bits is enough, and actually using a small number of bits is exactly what enabled us to build, to construct a near optimal algorithm for that. And we use programming for both the upper and lower bounds, which I find quite interesting in a theory paper. And let me tell you about a follow-up that we did in which we want to send vectors, right? So we have a d-dimensional vector and we want to send it with 1 bit per coordinate on average plus some small overhead. And this is a paper that's available on arXiv. And the highlight in this paper is that when we send vectors, we should first rotate the vectors, right? So we have some rotated vector Rx, and then we can send each coordinate in the rotated vector independently. So Angel gets some estimate of the rotated vector. Angel then applies the inverse rotation to estimate the original vector x. And the idea here is that the rotation is generated using shared randomness, so both Buffy and Angel can generate it without communication. So why do we do that? Like, why do we want to rotate x, right? So first, what it gives us is that the adversary cannot choose a bad input vector. And the idea is that after the rotation, the vector is going to land something that's pretty uniformly on the unit sphere. So in that sense, it cannot force us to have a large error. So any input would have the same error, right? Another thing that we show, which I find very interesting, is that we can actually use biased quantization when we send the rotated coordinates 1 by 1 and still get an unbiased estimate for the original vector. And finally, and this is because of the inverse rotation. And finally, unlike this paper where we optimized for the worst case input, we actually know what the coordinates are going to be distributed like after the rotation, so we can optimize for the resulting distribution. So I'm going to conclude with a couple of open problems. The first is, given a distribution on the inputs, how can we construct an optimal unbiased algorithm? And I'll just tell you that subtractive dithering is not optimal even for the uniform 0-1 case. And another problem is, how do we prove sharper bounds when we allow finite shared randomness, because all of our lower bounds allowed arbitrary shared randomness. And with this, I will conclude, and thank you very much.